All right, so if I now have a data structure called node, I can use it to kind of stitch together these linked lists. And maybe just to vary things a little bit and to start giving away some ducks, would folks be comfortable with volunteering to solve a problem here? Yeah? OK, come on up. 1, 2. Sure. Or you can take a duck and run. OK, 1, 2. How about 3? Come on over here. 3. So if you want to be our first pointer, come on, you can be number 5. Come on over here. You want to be number 9. And one more volunteer. Come on over here. Yeah. All right. So I'll meet you over here. OK, 17. All right. So if you'd like to, just so we pick this up for those following along at home, if you would like to just say hello to the audience.
Hi, I'm Andrea.
OK.
Hi, I'm Kami.
Hi, I'm Keon. Hi, I'm Jim.
Wonderful. OK, and if you wouldn't mind, I'll just taking a big step back over the ducks, just so that we're a little farther back. Let's go ahead and do this. If you're our first pointer, if you could come over here, for instance, and just stand outside the ducks. And if you guys could come a little over here in front, is still fine. So here we have the makings of a linked list. And what's your name again?
Kami.
Kami is our first pointer, if you will. Via Kami's variable, are we just going to keep track of the first element of the linked list? So if you could, with your left hand, represent first, just point over at, what was your name again?
Andrea.
Andrea. So Andrea is the number 9. If you could use your left hand to point at number 5, and if you could use your left hand, to point at number 17, and your left hand to just point at null, which we'll just call the ground. So you don't want to just point it randomly, because that would be like following a bogus pointer. So here means null. All right, so this is a linked list. All you need to store a linked list of 3 values is 3 nodes, inside of which are 3 integers, and their left hands represents that next pointer, so to speak. Kami's a little different in that she's not holding a value. She's not holding an integer, rather holding just the name of the variable first. So you're the only one that's different here fundamentally. So suppose I want to insert like the number 20. Could someone volunteer to be the number 20? OK, come on up. All right. And what's your name?
Eric.
Eric. Eric, you're the number 20. And Eric, actually, let's see. Actually, can we do this? Let me make this a little more different. OK, that never happened. OK, Eric, give me that, please. I want to insert Eric as number 5. So Eric, I'm keeping this list sorted. So where obviously you're going to go?
Right there.
All right, but before you do that, let's just consider what this looks like in code. In code, presumably, we have mallocked Eric from the audience. I've given him a value n of number 5. And his left hand is like, it's a garbage value right now, because it's not pointing to anything specific. So he's got 2 values, an integer and a left hand representing the next pointer. If the goal is to put Eric in sorted order, what should our steps be? Like whose hand should point where and in what order? Yeah, give us one step.
You should point to number 9.
OK, so you should point at number 9, which is equivalent to saying point at whatever first or Kami is pointing at. So go ahead and do that. All right, next. What's the next step? Someone else? Someone else. Oh, almost there, yeah?
First should point to 5.
OK, so first, or Kami, could you point to 5? And that's fine. You don't even have to move, right? This is the beauty of a linked list. It doesn't matter where you are in memory. It's the whole beauty of these pointers where you can literally point at that other location. It's not an array where they need to be standing back to back to back. They can be pointing anywhere. All right, let's go ahead and insert one more. Who wants to be, say, 55? Big value. Yeah, come on down. All right, what's your name? Keon, OK, so come on over. So we've just mallocked Keon from the audience. I've given him his n value of 55. His left hand is just some garbage value right now. How do we insert Keon in the right order? Where is he obviously supposed to go? In sorted order, he obviously belongs at the end. But here is the catch with a linked list. Just like when we've discussed searching and sorting in the past, a computer is pretty blind to all but just one value. And the linked list at the moment, like I don't know that these 4 exist. All I know really is that Kami exists, because via this first pointer is the only access to the rest of the elements. And so what's cool about a linked list, but perhaps not obvious, is that the most important value is the first, because from the first value you can get to everyone else. It's not useful, for me to remember Andrea alone, because if I do, I've just lost track of Kami, and more importantly, because of his number, Eric. So all I have to do really is remember Comey. So if the goal now is to insert number 55, what step should come first? No pun intended. Okay, say again?
Finding the first space.
OK, finding the first space. So I'm going to start at Comey, and I'm going to follow this pointer, number 5. Does 55 belong here? No. So I'm going to follow this pointer and get to Andrea. Does 55 belong here? No. I'm going to follow her pointer and 22, does it belong here? No. I follow this pointer, 26, no. But you have a free hand, it turns out. So what step should come next? We could have you point at 55, and now done. So relatively simple, but what was the running time of this? Yeah, it's big O of n. It's linear because I had to start at the beginning. Even though we humans have the luxury of just eyeballing it, saying, oh, obviously he belongs way at the end. Not in code. Like, we have to start at the beginning, traverse the whole darn list until we get linearly to the very end, and now we're done. Let's try one last one. How about 20? Yeah, right, come on down. What's your name?
James.
James. All right, James. All right, so we just malloc James, given him the number 20. He obviously belongs roughly in the middle. What's the first step? Sorry? All right, so we start with Comey again. All right, first, OK, 5. Do you belong here? No. Let me follow the link. OK, 9. Do you belong here? No. Do you belong at 22? Ooh, but what did I just do wrong? I went too far. At least in this story, like Andrea's behind me now. OK, so can I follow the pointer backwards? You can't. Like in every picture we've drawn and every example we've done with an address, we only have the address of the next pointer. We don't have what's called a doubly linked list, at least in this story, where I can just turn around. So that was a bug. So I need to start over instead. First, OK, 5, OK, 19. What I really need in code ultimately is to kind of peek ahead and not actually move, not that far, just to 22, peek ahead at 22 and realize, oh, that's going to be too far. This is not yet far enough. So let's go ahead and bring James over. Oh, actually, you can stay there physically. But what step happens to happen first? I know now he belongs in here. You want to point at him? OK, point at him.
First. Oh, sorry, he points first.
Well, let's do that just because it is incorrect. That's fine. OK, Andrea proposed that we point here, but she just broke the whole linked list. Why?
Because there's nothing to point at for him.
Right. No one is remembering. What was your name again?
Keon.
No one remembered where Keon was, so can't do that. Your left hand has to stay there. So what step should happen first instead? James should point at whatever Andrea is pointing at, perhaps. So a little redundantly at the moment, just like before. OK, now what happens next? That's step 1.
Now you can point.
Now you can point at him. OK, good, do that. All right, and so now this looks like a complete mess. But if we know that Comey is first, we can follow these breadcrumbs to Eric, and then to Andrea, and then to James, and then the rest of our list step by step by step. So it's a huge amount of like logic now, but what problem have we solved? And I think we identified it over here earlier. What was the problem first and foremost with arrays?
Mid-size.
You have to decide on their size in advance. And once you do that, if you want to add an additional element, you have to resize the whole darn thing, which is expensive because you have to move everyone around. Now, frankly, I'm being a little greedy here. And every time we've inserted these new elements, I've been keeping them in sorted order. So it would seem that if you insert things in sorted order, big O of n every time, because in the worst case, the new element might end up all the way at the end. But what if we relax that constraint? What if I'm not so uptight and need everything nice and like orderly and sorted? What if I just want to keep growing the list in any random order? And I allocate the number 34. And I'll play the number 34. Malloc 34. Where is the quickest place for me to go? Yeah.
Point to 5 and then have for
OK, I'll point to 5. And then Comey, if you could point to me. Done. 2 steps. All right, suppose now I malloc 17 with someone else who we'll pretend is right here. Where's the best place for 17 to go? Right after Comey 2. So now Comey can point at 17. 17 can point at me. I can point at Eric, and so forth. And that's 2 steps again. 2 steps. If it's the same number of steps every time, we call that constant time. And we write it as big O of 1. And so here, too, it's just a trade-off. If you want really fast insertions, don't worry about sorting. Just put them at the beginning and deal with it later. If you want dynamic resizability, don't use an array. Use a linked list and just keep allocating more and more as you go without wasting a huge amount of space, too. Which, notice, that's another big problem with an array. If you over-allocate space and only use part of it, you're just wasting space. So there's no one solution here, but we do now have the capabilities, thanks to structs and pointers, to stitch together, if you will, these new problems. Yes, please.
Why can't the no, like the one that's going to no, going to be, going to no?
And who am I in this story?
let's see if there's 41 let's say.
Oh, OK, absolutely. So another very reasonable idea would be, well, why don't I just put the new ones at the end? That's fine if I keep track of who is at the end. The problem is at the moment in the story, and we'll ultimately see this in code, I'm only remembering Comey, and from Comey am I getting everywhere else. I could have another pointer, a second pointer, and literally call it last, that's equivalent to you, or that's always pointing at you. I just need then two pointers, one literally called first, one literally called last. That's fine. That's a nice optimization if I want to throw all of the elements at the end. And frankly, I could get really fancy, and to solve the problem that Andrea cited earlier, if I store not just an int and a pointer, but instead an int and two pointers, I can even have each of these guys pointing with their left and right hands in a doubly linked list so as to solve the problem Andrea identified, which was if I go too far, no big deal, take one step back. I don't have to think as hard about that logic. So there too, a trade-off.